Okay, maybe we can start. So in the last lecture, we talked about symmetry and dual symmetry using Ising model as a very simple example. And we emphasize that it's better to put the symmetry, dual symmetry together and call this combination a categorical symmetry. And so they're not only these two symmetries describe two different conservation laws, one for the charge, another for domain wall. And then this combining two symmetries together also reveal there's an actual feature like a mutual statistics between these two symmetries. So and then we say that it's more convenient to use so-called patch operator to describe two symmetry. For example, for the Ising model, we have this the symmetry patch symmetry transformation is given by the product of X, but for the dual symmetry, just a two Z operator at the string end. But in the dual Ising model, the dual symmetry is a product of a Z. Then the dual symmetry, original symmetry is just two operator on the string end with empty bulk. So use this anyway. Using this patch operator, we can express two symmetry explicitly even within the same model. So this actual feature we talk about is this these two symmetry transformation do not always commute. So remember, one is a product of X, another is a product of just 2Z operator at the string end. So this is just in the Ising model basis, product of X and another is 2Z operator. So when the two string operators straddled in this way, they anti-commute because Z and X collide, so that's anti-commute. So this is the actual feature we mentioned that not only the conservation law and selection rule, there is a mutual statistics we can see from this operator. So therefore, to understand these two symmetries together, we should also capture this actual feature. So one way to do this systematically actually is to go to this holographic theory. That is, go to one higher dimension. Because in one dimension, we do not have a braiding. So mutual statistics is hard to say. But in one higher dimension, in two dimension, we can break. So this mutual statistics make more sense. Okay. So to really capture this actual feature in this operator algebra, so this we have operator algebra to capture this actual feature in operator algebra, then we can consider this Z2 gate theory. And in Z2 gate theory, it's kind of like a topological superconductor, basically. And yeah, there's four kinds of excitation. A trivial one, which is always there, is a one, means nothing, maybe identity operator or whatever. This is a local operator. And this non-trivial one with this E is a Z2 charge. And M is a Z2 flux. And E is a boson, M also boson. And there's also have EM bound state, which is F, and which is fermion. Okay. So actually this Z2 gate theory in one higher dimension happen to match what we want. For example, in the bulk, we have this mode2 conservation of E, which really corresponds to our symmetry. And this Z2 flux M particle also have a mode2 conservation, which happen to correspond to our dual symmetry. Okay. And then E and M have non-trivial mutual statistics, this mutual pi statistics. That's exactly the actual feature we want to capture. You know, this configuration, if you view this operator order as a time direction, then the different operator orders like a different time direction, a different time ordering, then it's almost like a braiding. So this is the motivation. So and it seems if you go to one higher dimension, a Z2 gate theory, that's a more fully capture these two symmetry plus dual symmetry. I think that's a really main point. And this feature actually may be general. So that's a proposal. It's a very general feature. For any symmetry, we can do this. And we get a little bit of extra because this EM bound state have this F. F also have this model conservation. So we have this Z2F symmetry, which is conservation of Fermionic particle. Okay. So in some sense, this Z2F symmetry is maybe anomalous. It's a it's a Z2 symmetry, but it should be different from this Z2 symmetry for the boson. And this particle is fermionic, so it has some extra features. Okay. So it's very tempting to say this Z2F symmetry is anomalous. Yeah. But we are doing one-dimension theory. In one dimension, the standard theory for Z2 symmetry, anomalous Z2 symmetry, is that there is no anomalous Z2 symmetry in one dimension. So it's really this reflect our previous understanding of anomaly is kind of limited. We understand anomaly in some way. Okay. And using this holographic picture, we have a more general understanding of anomaly. So in a sense, this Z2F symmetry can be viewed as anomalous. Or maybe you can say it's something else. You can also say this is beyond anomaly, beyond the standard definition of anomaly, but something different. It just and view this as something like anomalous is reasonable because it has some symmetry abstractions actually. But let me go to say. Okay, so this holograph picture also unifies this patch operator. So under this holograph picture, the patch operator all put in the equal footing. This, remember we have patch symmetry operator, which generates symmetry locally, and the patch charge operator, which create a pair of charge. In this holograph picture, these two operators became roughly the same on equal footing. And this patch charge operator, it just create a pair for E. So it's really corresponds to this string operator in the bulk, which create a 2E particle. Remember, in the bulk, we cannot create an E particle alone. Like in topological model, we have to use a string operator to create a pair of E particle. And when you bring this string operator near the boundary, this string operator became this patch charge operator, which created a pair of charge at the boundary. It's really corresponds to this operator. And then in the bulk, similarly, we also need a string operator to create a pair of Z2 flux. Then if you bring that operator to the boundary, that should correspond to this kind of patch symmetry operator, which is product of a bunch of X. Okay. And certainly this operator representation depends on the model. Like the icing model and the dual icing model, they have a different representation. So in the dual icing model, this operator would have a non-empty bulk, and this operator would have empty bulk. And similarly for the dual symmetry, then for dual symmetry, patch charge operator for the dual symmetry is same as the patch symmetry operator of our original symmetry. So again, it corresponds to string operator of creating ants. So basically, that's another thing that so in the bulk we have all kind of string operator creating those bulk extensions, and those string operator became patch operator on the boundary. So this analog again is very general. So it's applied for all the symmetries. Okay. And so now here we are asking, if you say that the symmetry is described by something, a topological order in one higher dimension, so what that really means? The meaning is really that the symmetry constrains the dynamics of a symmetric system. And similarly, topological order also constrains the dynamics of its boundary. So it is in this sense, these two things are related. Again, this is also a very general statement, although we consider a very simple example. So here we claim that every symmetry can be simulated by topological order in one higher dimension. And in this sense, and the topological constraints dynamics boundary and symmetry constraint dynamics of the system. Okay. And this simulation apply for symmetry, higher form symmetry, and non-invertible symmetry, or normal symmetry, so every symmetry, and even maybe some new symmetry we don't know. But we can, using this simulation, use this definition to define what the symmetry means. Topological order means symmetry. So we can say all the symmetry kind of correspond to some topological order. So this became very general and unified picture of all the symmetry, and all kind of symmetry. So to really see the boundary, then it's that we can consider the following thing. Let's consider just a condensation of E particle in this Z2 gauge theory, and that's just Higgs phase. We'll condense the E particle. Then in the condensed phase, the E particle disappeared. It's just absorbed by the vacuum. So E particle just disappeared. And M and F particle also disappeared, because when M is like a vortex, a flux for the E particle. If E particle condense, this M particle would insert a branch cut, which cause finite energy linearly in the length of branch cut. And so therefore, the two M particles would have linear potential between them, and they are confined. So there's nothing. So therefore, this condensation of E particle give us a trivial topological order. Actually, in some sense, this introduces a notion so-called the condensable algebra. This is kind of fancy name. The condensed algebra basically is a collection of onions that can be condensed together. Okay. That's also introduced a notion of a Lagrangian condensed algebra. That is when the condensed algebra is a Lagrangian, means that those not only those onions can condense together, we have enough of those onions. So after the condensation, you get a trivial phase, you get trivial topological order. So Lagrangian is like a maximum condensed algebra. And if you condense very smaller after condensation, you still have something left, some topological extension not confined. And then so then the resulting condensed phase is not trivial topological order. Okay, so that is so that's kind of more general notion. Okay. Then in this picture, you can see that then the main wall between this Z2 gauge theory and the trivial topological order basically is a boundary. It's basically given by the condensation. So this describing is really big. It's really trying to say that a boundary of a topological order can be viewed as a domain wall between topological order and the trivial phase. And the trivial phase is induced by condensation. So from that sense, we say domain wall is induced by condensation. Yeah. So domain wall and the condensation are very much related. Okay. So this is using this picture. We say that, for example, like just described, we can condense the E particle to get a trivial phase, and there's that domain wall between that trivial phase and this Z2 topological order is basically induced by E condensation. And more generally, you can also say one part, trivial part always condense. So always condense. So condensed algebra is a 1 and an E. So these two form a condensed algebra. We condense this collection of onion and form a boundary. And obviously, in this boundary, E condensed. So E is absorbed at the ground state. This is very much like a spontaneous symmetry breaking state of this Z2 symmetry. The charge is absorbed by ground state. And then the domain wall is M is domain wall. Domain wall remains have this finite energy gap. And it's there, it's as an extension. So therefore, this E condensed boundary corresponds to this the phase where we have this correspond this phase. Z2 spontaneous symmetry breaking, but the dual Z2 is symmetric. Oh, I think this is a mistake. So then we can have the other one is that is M condensed. So here this is as a wrong figure. It's another figure. So we have M condensed. So you have a M condensed. Then the M is absorbed by the boundary. So that corresponds to the spontaneous breaking of a dual Z2 symmetry. But this is then E is not condensed, so there's the E symmetric, so Z2 symmetric. So that is this phase. Okay. Again, this is a very general feature, is that the different phase is coming from different condensation. Okay. So actually so we can change our classification of phase into a classification of condensed algebra. We say within this categorical symmetry picture, we can really obtain what can condense together. And the thing that can condense together in a bulk gave rise to all different boundary phase. And this led to another way to classify all different phase. And this classification, I think, is more general, more systematic, because it's applied to any symmetry, even non-invertible symmetry. And also the resulting phase can be symmetry breaking phase, as we discussed here. But sometimes we also obtain SPD phase this way. Actually, certain condensed algebra gave rise to SPD phase. We do not get SPD phase because of the in one dimension single Z2 symmetry don't have SPD phase. But when you have SPD phase, that's when you have this Z2 cross Z2 symmetry. Then their categorical symmetry will be Z2 cross Z2 gate theory in one higher dimension. And then we can study all the condensed algebra for the Z2 cross Z2 gate theory. And all their condensed algebra is easy to compute in this case because they are abelian topological order. Condensed algebra basically means a collection of anions, which have a trivial mutual statistics and a trivial self statistics. And we have enough of them, so we have a maximum of them. We cannot expand this algebra further. And there are several this maximum Lagrangian condensed algebra, and which gave rise to symmetry breaking states, symmetric states, and SPD states. Okay. And so in one partial dimension, that's a story. I think in higher dimension, we believe this is also true, but there you can even get a topological order state, SET state. All this probably can be obtained this way. But the formalism of higher dimension is more difficult. Okay. Yes.
So even if I take this periodic boundary conditions,
yes,
the C2 dual symmetry still makes sense as long as I look at this patch symmetry variables. Like in principle, the symmetry for periodic boundary conditions.
Yeah, it still makes sense, and it's really like this. You can see in the original model, the dual symmetry transformation is just two operator on the boundary. When you have a model with periodic boundary condition, when you apply this, when you consider dual symmetry on the whole ring, then these two boundaries kind of annihilate. They get nothing. So the symmetry transformation became trivial. So this trivial symmetry transformation looks like there's no symmetry. Yeah. And but I try to say that the other way. I say, yeah, we have the symmetry, but in this particular UV regulation, in this particular lattice model, there's no local operator can break the Z2 dual symmetry. But however, in the dual model, in dual lattice model, then we have a local operator which break the dual symmetry, but we don't have any operator which break the original Z2 symmetry. So from these two, you can see that there's some duality here. Yeah, and certainly, yeah, this is a very good question. You know, here we really take a point of view that we really putting two symmetries together, thinking them together, think them both present, rather than choosing a lattice model, only think one of them are present. The difference is that when you're choosing lattice model, think one of them are present. This is like a regulation dependent. This point of view depends on how you regulate the theory. how you choose your lattice model. So you can imagine you have a field theory. You don't know what is a UV regulation. Then when you're choosing different UV regulation, you actually get different picture. One symmetry is legal, another is illegal. But when you have when you don't think about the lattice regulation, just in general think of the UV phenomena or infrared phenomena as a field theory. I feel it's more convenient to think both symmetry are present. And then we introduce a patch symmetry operator, really try to emphasize this. Yeah, they both are there, and we can see their structure. It's a little bit strange, you know. The traditional point of view really just think about half a symmetry. We don't think the two symmetries together. Here we really thinking symmetry, dual symmetry together. And it's really because of the locally, if you don't think about it's locally, you really have two mode conservation, one for domain wall, one for the axis spin. You really have two locally, really have these two mode conservation. Yeah. And I just find this point of view is more convenient, you know. So I kind of persuade this point of view. But this indeed tricky, you know. I think the point is that you don't have to think this way. You know why you think this way? You don't have to. And I probably cannot have a proof that you have to think this way. Maybe for the moment it's more convenience, and but you do get a more global, more general point of view. Maybe let me put this way. Later I will talk about this. We will think about this way, putting symmetry, dual symmetry together at equal footing. Think about the holographic way. You'll find that we have this S3 symmetry, this permutation of three elements. This a transition from S3 symmetric states to a complete symmetry breaking state, which is Z1 state. This transition is same as from the subgroup Z3 to Z2 transition. So when you have this S3 symmetry, this S3 symmetry have four different subgroups. Is the S3 itself a trivial subgroup Z1 and Z2, Z3. So there are two symmetry breaking patterns. Those symmetry breaking, complete symmetry breaking, break down to Z3 or break down to Z2. The claim is that the transition from S3 to Z1 is due to Z3 to Z2. If one transition is continuous, second transition must be continuous. If one is first order, second must be first order. So this holographic picture allow you to see this more easily. So that's maybe the convenience. And certainly in this IC model, maybe one don't have to think this. Okay, IC model we know everything. We don't have to think this fancy way to know everything. But the holographic picture I think had an advantage. Yeah.
So given the topological order in the book, is there a way to derive the boundary theory, particularly get a tensor product Hilbert space and to get the local Hamiltonian terms?
Yes. And yeah, since you mentioned this, let me just draw this. And so here you can see that okay, yeah. So here only consider, maybe you can just here only consider one boundary. And you can consider another gapped boundary here. Then okay, what I try to say is following. You can see here we consider let me just here we just think a system with a bulk, given one boundary. And this point of view is like consider the boundary ignoring its lattice cutoff, ignoring this 1D system. Just view this as a low energy effective theory, as a local theory. But to really construct the full lattice model, and you can add another gapped boundary. When you add another gap boundary, this whole slab, you can view as a one-dimensional lattice model. Then you get a complete theory. Then by choosing different gap boundary here, you get different version of a lattice theory. Actually, by choosing the M condensed boundary or E condensed boundary on the top, you really get a Ising model or dual Ising model. And so if you only look at the one boundary without seeing the other boundary, it's like, well, ignore the lattice cutoff. Just look at it more like a field theory point of view. And but to get a full theory, one need to supply another boundary. Yeah. So yeah, I may not really direct answer your question, but this maybe some related. Yeah. So later maybe I'll also come to this. Yeah. So this so therefore so this picture is like by drawing this picture, you're actually doing lattice model without writing down lattice by adding another boundary. Then you get a complete theory. Okay, and so but then there's yet another very interesting thing from this holographic picture for the symmetry. So you can see this we have a E condensed or M condensed. E is like a charge, M is like a pi vortex in superconductor. Okay, and we could have a boundary which have nothing condensed. We don't have anything condensed. Okay. And before we don't know what is this boundary is. If because we need some condensation to get a trivial phase. Then we get a boundary. If nothing condensed, the other side is not a trivial phase. But we insist that we have a trivial phase other side, but the boundary have nothing condensed. And so we say this thing exists. And from topological point of view, it seems hard to imagine if nothing condensed, what you might you have a boundary, you know. But from 1D system point of view, this is very natural. It's just a transition point between these two condensation. There's E condensation, M condensation. Okay. And we want to say that the E condensation, M condensation are mutually exclusive. We cannot condense both E and M together because they have non-trivial mutual statistics. Only boson condense together, but not two particles with non-trivial mutual statistics cannot condense together. So therefore, we can imagine first we have E condensation, then we try to bring M to have low energy on the boundary, try to make M condense. When M try to condense, you try to like competing order, we try to push Z condensation away. So then the E condensation become weaker and weaker. M condensation, M want to condense maybe stronger, and eventually at some critical point, the both E and M do not condense. Then go over that, E do not condense, M really condense. So you can see that there's this transition point. The continuous transition is really the point where E and M competing and they kill each other. They both do not condense. So therefore, this led to this intuition. If you do not condensing, we have a boundary. We're not condensing anything. This boundary actually is gapless and it is describing critical point. So again, this is another intuition obtained from holographic picture. That is not only this Lagrangian condensed algebra, there is a maximum set of condensable anion, classify the gapped phase in one lower dimension. Then if you don't condense maximum set, condensing only partial set of anion, you actually describing the gapless system, the gapless states. So that's it. That's again, it's a very simple example. It demonstrates this very general principle. The gapless states correspond to condensing maximum set of condensed algebra. The gapless states correspond to condensing non-maximum set. Then we may have a classification of a gapless state as well. by condensing just a partial set of a smaller condensed algebra. Certainly, the smallest condensed algebra is just trivial. We don't condense anything. Then that gives you the maximum gapless states. Yeah. So this is this really gave us some kind of a very general picture from symmetry, from their corresponding topological order in one higher dimension, and from their condensed algebra. Then we go back to a lower dimension. We got the understanding of gap space and the gapless space. Yes.
So you were mentioning that if you want to fully describe the holographic picture, then you need to consider all of the boundaries, right? But in this case, you only consider one boundary. If you take into consideration of the other boundary, what would happen?
Yeah.
When you have some states that both they do not condense on one boundary, what about the other boundary?
Yeah, and the other boundary is in my description a moment ago, we're kind of ignoring another boundary because we consider only so-called local low energy property. The other boundary assumed to have a large energy gap. If you consider low energy property, we can ignore the other boundary. But however, the other boundary also have large energy gap, but other boundary may have a ground state degeneracy. So when you think about the sectors, when you have a ring, you say, well, the ground state is a 2-fold degenerate, 3-fold degenerate, those kind of global properties. Then you have to consider the other boundary. However, if you ignore the other boundary, only consider local property, like in this segment, whether some local operator have what is a correlation function. And so those kind of local low energy property do not depend on the sector. Then you can study that without consider other boundary. And but as a more detailed global picture, you need to include other boundary. And here I really taking a point of view that since here we are interested in the gapless system, we are more interested in the local low energy property, which makes things simple. When you consider sectors, you have more features, so more complicated. So when you think about the local low energy property, that's the most important thing for gapless system. And so then we can concentrate on the bulk and the one boundary, ignoring other boundary to make things simpler. That's basic. Certainly to have a full theory on the regulated lattice, you do need another boundary. Yeah, but we purposely ignore that just because we concentrate on gapless states. Okay. Yeah, so this basically, I think this may be the main message here is that the bulk topological order and their condensed algebra gave rise to our new picture of a gap and the gapless states. And there's a chance we can classify gapless states from this point of view by studying non-maximum condensed algebra. Actually, maximum condensed algebra can classify gapless states. Okay, so this really this picture we just I just said. So the main thing is that we have this symmetry breaking state for symmetry of the dual symmetry and etc. But the symmetry breaking state, a spontaneous symmetry breaking or symmetry can be measured by the correlation function. They really offer that the long range order. Because we want to, because in our story, this in the duality story, these two models are really equivalent or identical only within the symmetric sub-Hilbert space. Okay, so we want to study symmetric sub-Hilbert space, and it is only this symmetric sub-Hilbert space is simulated by the one boundary of a bulk. If you only consider one boundary, you only simulate the symmetric sub-Hilbert space. You don't have other sectors. To have other sectors, you have to put the other boundary. Maybe I can explain that later, but here the main thing is that, for example, on this boundary, we can only create a pair for E operator on this boundary. it's really the following. Because in the bulk, suppose we only have one boundary, then the E particle always appear in pairs. If a bulk have very high energy, and the E particle may have low energy on the boundary, then you either have one E particle on the boundary or another E particle in the bulk, which have very high energy, or we have both E particle on the boundary, which have a low energy. So therefore, low energy subspace really have always have even number of E particle. So that is symmetric subhero space, and so therefore in this symmetric subhero space, we cannot consider average order parameter to see whether order parameter is equal to 0 or non-zero to see whether symmetry breaking or not. We have to consider the creation operator of two charge pair, which is total neutral. And the average is a two creation operator. It's really this correlation function of order parameter. When they have a alpha diagonal long range order, then we have this symmetry, so spontaneous breaking. If they have a exponential decay, that symmetry is not spontaneous breaking. And so actually, we can also see that in all these three phases, this Z2F symmetry, I think they have this exponential decay. So this symmetry is always there, not broken. This is Z2F. But for Z2 and Z2 tilt, one is broken, another symmetric. Okay. But here really I try to emphasize that the two symmetry cannot break together. You can break one or break another, you get gap phase. And they can be both unbroken. They are both symmetric, it must be gapless. Okay. So this actually is in this Michael Levin's paper in 1919, the rigorous proof that yes, the order parameter, disorder parameter, if both order parameter or disorder parameter is not constant, the theorem must be gapless. So there's a more rigorous proof. So it's really, but it really says that the state with unbroken categorical symmetry must be gapless. Okay. And from this, this actually give us a general picture of symmetry protect or symmetry enforce the gaplessness, because basically it says following. If a categorical symmetry is not broken spontaneously, then the state must be gapless. Okay. So in our example, we have this EMF, we have a three particle. If we have a mode conservation of all three, and all three is not spontaneously broken, then this must be gapless. Okay. So this is a kind of a very general way to understand the symmetry protect the symmetry enforce the gaplessness. Okay. But actually this result can be phrased more generally. When people say a symmetry protect a gaplessness, they do not mean this symmetry is a full symmetry. It's not full categorical symmetry. It's maybe only partial. So what I mean is really following. And sometimes we do not need to enforce the full symmetry. We just say if a symmetry or normal symmetry, or maybe more correspond to this partial categorical symmetry. If a partial categorical symmetry is not broken, not spontaneous broken, sometimes that's enough to protect it and enforce gaplessness. And this is usually when people say certain symmetry or anomalous symmetry can protect, enforce gaplessness, people usually refer to a partial categorical symmetry. Okay, what I mean by that is that the full categorical symmetry really is like an EMF. And this EMF from a complete set of onion in a topological order. So that means that's a categorical symmetry. Categorical symmetry contains all the onions in a topological order. We have a so-called partial symmetry. They have subset of onions. We do not consider full set. For example, let's consider this just E and M. if you only consider E and M, these are two mode-2 conservation, and that one is enough to enforce on the gaplessness. And in our language, it's pretty simple because in the bulk, the E and M, they can fuse. They fuse the generator F. So therefore, although we consider subset anion, only subset of a symmetry, but this subset is big enough to generate all other anions, all other symmetries, then that's enough to protect gaplessness. Okay. So when I say an E and if we only refer to E and M conservation, then we say that we have a two Z2 symmetry, two mode-2 conservation of two bosons. Okay. Will protect and enforce gaplessness, provided that these two bosons have actual feature. They have a non-trivial mutual statistics. So then we have a two conservation of a 2Z2 conservation. You don't enforce gaplessness. You could have symmetric gap states with both Z2 conserved and symmetric. But however, when you have a two unbroken Z2 symmetry with a non-trivial mutual statistics, then it's important enforce gaplessness. And then we understand this because the E and M is enough to generate everything. Similarly, we can consider E and F. So that means we have a conservation for one boson, mode-2 conservation of a boson, and the Z2 conservation of fermion. These two is enough to generate to protect the gaplessness. Again, provided that they have non-trivial mutual statistics. Without this actual feature, they don't protect gaplessness. Okay. And again, this is very general. You know, so this non-trivial mutual statistics actually correspond to anomaly, really. This actual feature really corresponds to anomaly. So from here, you can see that if you only consider a mode-2 conservation for E, okay, and there's no anomaly, so that's just a Z2 symmetry, and they do not protect gaplessness. Okay. However, if you pick but however, this Z2 symmetry already imply the categorical symmetry of EMF, already imply all three. And if you insist on this, two of them, say E and M, do not break. And then you say that if you look at the two E and M, then you have anomaly. That's what I say. Let me say it again. Sorry. If you only look at the E, the Z2 symmetry for the E conservation already implied the full categorical symmetry. But however, if you only look at the E conservation, it's anomaly free Z2 symmetry. For the same categorical symmetry, you can view this as a Z2 symmetry, E and M. And that corresponds to anomalous Z2 symmetry. Or you can view this as a Z2 symmetry for E and F. Again, that's anomalous Z2 symmetry. So actually, anomalous symmetry is just a choice. You just pick some part of a categorical symmetry, this is anomalous symmetry. And so that's why I feel this viewing this categorical symmetry, the full thing is more convenient. It's more systematic. And just look at anomalous symmetry, anomalous algebraic symmetry, all these things, it's just a point of view. It's a very inconvenient. So now I try to avoid using anomalous symmetry. But whenever I need to use anomalous symmetry, I try to go to a categorical symmetry and to get the whole picture. Yeah. Okay. So yeah. So this example try to demonstrate when you have a full categorical symmetry, you can take a part of it. The part of it can be anomalous symmetry, can be anomaly free, and sometimes a part of it is enough to protect, enforce, and the gaplessness. And this is a very general way to understand the symmetry protect and enforce gaplessness. I'm not sure whether all the symmetry enforce gaplessness can be understood this way or not, but the manyest example I heard about can be viewed from this point of view. So this is like a general, universal way to understand this gaplessness. Okay. Okay, so now we can consider something more general. So here we try to say that I hope I convince you that the categorical symmetry, this holographic way to view symmetry is useful at least. Okay. So therefore, for any given symmetry or given anomalous symmetry or with any system or something, we want to calculate this categorical symmetry, calculate this topological order in one higher dimension. Then we get a more general way, point of view of a symmetry, more global view of symmetry. And there's one simple situation. Suppose we have a symmetry, anomaly free symmetry described by a group G, or some higher group, can be higher symmetry, something like that. Then how to compute this categorical symmetry? And because we have an anomaly free symmetry, and then we can view this anomaly free symmetry system with anomaly free symmetry as a boundary of a trivial product states. Okay. And then we gauge the trivial product in one higher dimension. Then we get a gauge theory. Okay. So then we get just like that. Then we find that the categorical symmetry is just a gauge theory of same gauge group in one higher dimension. That's it. By gauging in one higher dimension, you actually automatically recover the dual symmetry. That's a way to recover dual symmetry. And also recover the actual things, because the symmetry, dual symmetry, they have non-trivial mutual statistics and etc. So those actual structure are all there. Okay. So this is one way. And then, however, what happens if you have an anomalous symmetry? So we have a system with anomalous symmetry. Then anomalous symmetry can be viewed as a boundary of SPD states in one higher dimension. Although on the boundary symmetry anomalous, we cannot gauge it. But the bulk SPD states, the symmetry is the onset symmetry, is anomaly free. And you can gauge the symmetry in the bulk. So when you gauge the symmetry in the bulk, and then you get this you get a so-called twisted gauge theory, which is called a Daggra-Witten theory. Okay. And so therefore the categorical symmetry for anomalous symmetry is naturally this Daggra-Witten gauge theory. Okay. Again, we get the symmetry, dual symmetry, and all these actual features is automatically in this bulk topological order. It's all included. So this is kind of a holographic calculation of this categorical symmetry. And also we can have this from this holographic picture. We also discover something new. That is, we can have a beyond group symmetry. There's some symmetry which is not described by group, but beyond group. And this is achieved by consider the non-abelian symmetry. If G is non-abelian group, like S3 group, or some dihedral group, some kind of Platonic group, so some non-abelian group. If G is non-abelian group, then their dual symmetry, the dual symmetry is a beyond group symmetry. From a holographic point of view, you can see that the gauge theory in the bulk have a particle-like a charge, which describe a representation of a gauge group. So that's just ordinary symmetry charge. Symmetry charge are labeled by the representation of a symmetry group. So the charge, strictly speaking, is a representation for non-abelian group. The different charge means different representation. Okay. Okay, and that's for the gauge theory in one higher dimension. We have a charge described by representation. That's really the ordinary charge. But we also have a gauge flux. Okay. In 2+1 dimensional bulk, the gauge flux is point-like, so still like a point particle. And but in higher dimension, in 3-dimensional bulk, this flux can be loops or can be membrane even in higher dimension. Okay. So those kind of flux point or flux line, they also have their fusion rules. They don't fuse arbitrarily. They cannot be created. They cannot be created from nothing. you know, and so they have non-trivial fusion rule. This non-trivial fusion means that they have some conservation. There's certain this always certain conservation law. So this conservation law from this gauge flux is really correspond to dual symmetry. And it turns out that this dual symmetry is beyond the group. So we call this algebraic symmetry or algebraic higher symmetry. If the charge is a loop, then we call this algebraic one symmetry. If charge is a point, we call it algebraic symmetry or zero symmetry. Yeah. So so this is I think this is a simplest example of a so-called non-invertible symmetry. Yeah, this symmetry also called a non-invertible symmetry. So there's a many names. Also called the fusion category symmetry. Okay. And so there's all kind of a name for this. Okay. So let's look into this more carefully. So what is this algebraic higher symmetry or non-invertible symmetry? So let's go very quickly, and so let's consider a non-abelian symmetry first, zero symmetry. So on every lattice site, we have a state labeled by the group element. So this G is labeled as group element. Okay. And then we can have a symmetry. The symmetry action is that we apply symmetry, again, symmetry labeled as group H, group element H. Then when WH acts on the state, we just right action, we multiply to the right all this H. So this so on every site, this group element changes. So that is symmetry action. Okay. Then from here we can get a set of local symmetric operators, which commute with this symmetry. So then this local symmetric operator from algebra that's describing our symmetric system. Okay. And for the symmetry we considered, here that this local symmetric operator have two forms. One is just this delta. And this combination, delta function of a G at the site I and a G at site J with inverse. This delta function is a symmetric operator, commute with the symmetry. And another operator also commute with symmetry is that first we have a TH. TH basically is doing the local transformation. So TH doing this way. THI just multiply H to the left on the single site I site. So TH is just a local transformation. Then we sum over all H, and this operator commute with again commute with symmetry operator. So these two operators are symmetric. And then we can construct Hamiltonian using these two operators, like the sum of this delta and the sum of T, then to get a symmetric Hamiltonian. Okay, so this is the one way to get this to get a Hamiltonian with a G symmetry. Okay, so this is the kind of preparation. Then once we have this particular Hamiltonian, we can do this. That's amazing. The non-abelian duality. You can do the duality transformation to get a dual model. And the dual model, instead of degree freedom on the site, now we have degree freedom on the link called GIJ. The degree freedom on the link. Then the relation between two models is really the following. The GIJ correspond to this GI times GJ inverse. So so therefore that's the operator mapping. We can view this as a operator mapping. So remember this. So we have an operator which is a delta function of the GI times GJ inverse. So this operator is a map into this delta function of GI. And because we have this mapping, and then this T operator, which originally act on a single site, now also act on the site, but now our degree freedom live on a link. So what they do is that for any link connect to set I, they get some change. If I in the to the left, we get H action. If I in the right, we get H inverse action. Something like that. Okay. So therefore we can map this the set model, into the link model from this using this operator identity. And it turns out that these two models is identical, have the same spectrum. Again, within the symmetric low energy subspace. Okay. But what is the symmetry? For the side model, we know the symmetry. Symmetry just this H action. For the side model, what is symmetry? Well, the side model have the following symmetry. Let me say that. For the side model, it turns out that it have this. Oh yeah, there's one thing I forgot to say. Actually, there's another constraint. This delta ijjki. That's the product of three link operator around the triangle. This product must be identity, because in a set model, the gij coming from gi and the gj inverse. We multiply this operator together around the triangle. It's always equal to identity. So therefore, this gij also should have this flat connection. So we need this operator. So then these two became equivalent. Okay. So anyway, so what I really try to say that maybe I won't go through this very carefully. Is that we actually have a operator, which actually is a Wilson loop operator, which is a product of gij. But however, it's not just any product. Is that we first pick a representation. This RQ is a particular representation of the G. It's some matrix. And then we construct a function of a gij, which is I put this representation and multiply this representation around the loop. Then take a trace. So this is really just a so-called Wilson loop operator. If you view gij as a gauge potential on the link, this is a Wilson loop operator. And this operator turns out to commute with this Hamiltonian, because for delta g term, they're both a function of g, so they commute. This T operator is tricky. They may not commute. But remember what the T operator do is T operator like doing something like that. When you have this like I have a link from I to j. Oh, sorry, j to I and I to k. So we have something from j to k. Then have a j to I and I to k. But then the product of these two operator, when you do the transformation of this T operator on the j side, then we have H inverse and H here, and the product of these two variable they would cancel. So basically, in the Wilson loop operator, they are strings. So like when you do the transformation here, then the RQ on this side and the RQ on this side, they both receive a transformation, but these two transformations on this link cancel each other. So therefore, this Wilson loop operator is invariant under this T transformation. So therefore, this operator commute with this Hamiltonian. So therefore, this is what we call the higher symmetry. It's algebraic n-1 symmetry. So this operator is kind of funny. Usually a symmetry acts on every side, but this symmetry only acts on loop. No matter how high spatial dimension, this operator always acts on loop. So this is called the n-1 symmetry, because the loop in n-dimensional space, this loop have n-1 codimension. So the level of symmetry is measured by the codimension of a symmetry transformation. So therefore, this Wilson loop operator basically generate this algebraic higher symmetry. And we call this is this non-invertible really because the composition of two symmetry operator, like we have a one loop multiply another loop, so the two loop coincide. You don't get the Wilson loop operator in a third of a different representation. So this Q is a representation of this of R. So suppose we have a Wilson loop for the Q1 representation, a Wilson loop for the Q2 representation. When you multiply together, you don't get a Wilson loop of a Q3 representation. Because when two representations put together, they decompose as a direct sum. It's not like a spin one half, a spin one half, spin one half. You get spin 0 and spin 1. You do not get single representation. Okay. So therefore, at the end, we find that the algebra of symmetry transformation is this one. When they fuse, they get this coefficient Nijk or NQ1, Q2, Q3. So like a fusion rule, we started before. Okay. This non-trivial fusion rule is not, this is not like a group, it's not group product because we have sum, it's not group. And so this kind of fusion, so that's, we call this fusion category symmetry. We say this is algebra, so we call it algebraic symmetry. So that's kind of where the name comes from. Okay. So this, so therefore, this is really the example of this the symmetry beyond the group. Yeah.
Are the n are negative as well?
What?
The n Q1, Q2, Q3 are they real numbers?
Oh, this n is an integer and a positive integer. Non-negative integer, they can be 0. So they really come on the fusion of two representation. It's really like this. When you have a spin one half fuse with spin one half, you get a 1 and also get 0 and 1. So this Nijk just say you have 1 0, so this that is 1 there, and 1 1, so that's also 1 there. So this is just a non-negative integer. So it's very much like the fusion of onions. So the fusion onion have the same thing. So this is very much like that. So actually, indeed, this is really like a fusion onion in the following sense, like maybe in this picture. So in 2 plus 1 dimensional box, so we have one plus 1 dimensional system with 2 plus 1 dimensional box. The gauge flux are really these onions. These M onions. For non-abelian group, this M onion have non-trivial fusion. The fusion of non-trivial M onion is quite different. It's quite non-trivial. Yeah. Okay. So this is just they give rise to this algebraic symmetry, and so we basically complete our story. That is from this holographic picture. We think there should be this conservation flux, gauge flux as well. We should have something more non-trivial. So indeed, we can construct a lattice model. So this is really this is really a lattice model, which indeed you have this one form symmetry, but not quite one form because it's not group, like it's not higher group. So we have we call it one symmetry or two symmetry and etc. Yeah. So basically, this really says that if this model in the 2-dimensional space, then this symmetry will be one symmetry. In 3-dimensional space, a similar model would give us a 2 symmetry and things like that. Okay. So, but this symmetry is really motivated from this holographic picture. It's there, then it's there. But certainly, but this particular kind of symmetry is motivated by this topological order, which is described by the gauge theory. But there's many topological order which is beyond the gauge theory. Now you can imagine, there's all kind of algebraic higher symmetries, but they all can describe by topological order in one higher dimension. So that is kind of more general unifying picture. Okay, so now let's so any question here? Yeah. So this is maybe just a very brief introduction of what is algebraic higher symmetry or some non-invertible symmetry. It's in this language, it's just a dual of a non-abelian symmetry. But for the abelian symmetry, their dual is also always higher form symmetry. So it's invertible, not non-invertible. Okay. So let's go back to our previous question. How to compute categorical symmetry for some beyond the group symmetry? Remember, before we say you have symmetry described group, we can compute the categorical symmetry by gauging in one higher dimension. But more generally, when you have a symmetry which we don't know is described group or not, or maybe it's something described by something beyond the group. So how to really describe its a symmetry? How to compute its a symmetry? So this is led us to this local operator algebra. I think this is a more general way to look at the symmetry. Remember that the symmetry is really about this about the selection for operator. Symmetry is not about the transformation. Symmetry is about a way to select a set of operator. We call the local symmetric operator. And those operators are so-called allowed operation. We can use these operators to build Hamiltonian, use these operators to do the measurement, and etc. So symmetry is really about a consistent way to select a set of operator. Then we use this set of operator to do whatever we want. Okay. So therefore, our input data is so-called the local symmetric operator. But the symmetric not necessarily described by a symmetric group, but by something, by some rule. Okay, here using symmetry just for historical reason. It's just some set of a permissible operator, you can say that way. Then we have this algebra of a local permissible operator. Then from this algebra, we should recover the symmetry. And we should recover this categorical symmetry. Means we should recover topological order in one higher dimension. This looks like string, from the operator algebra. How do you compute operator in one topological order in one higher dimension? How do you do that? And so the idea is really the following, which I'm going to present. First, because the algebra of local symmetric operator also naturally include the algebra of an extended operator. Because our space is extended. So we have many local operator, but we can multiply local operator side by side, then to build the operator with big size. Because operator algebra closed. So therefore any operator can put together, you can build a extended operator of arbitrary size. You can wind the system several times, So therefore, the algebra for local symmetric operator naturally include the algebra of extended operator. So you have to include them. Then this becomes too wild. We don't know what to do. It's just it's a mess. Then here, I think the main thing is that this step. Instead of consider generic extended operator, we consider a subset of extended operator. We call it transparent patch operator. I should put a patch here. This is a subset of extended operator we call the transparent patch operator. And this transparent patch operator is much more manageable. And from this algebra of transparent patch operator, we can derive this braid diffusion category. And so these two steps are very close, which I will explain. And then the braid diffusion category basically is a mathematical structure described onions, or maybe onion with string like onion, things like that, which basically became a topological order in one higher dimension. Yeah. So this is the steps. I think key is this introducing this transparent patch operator, which make calculation manageable. And so let's try to say what is a transparent patch operator. First, what is a patch operator? Patch operator is just a product of many local symmetric operator. Okay. And here we have product, but there could be a sum of several products. So this is also fine. Yeah, this is actually this headache. You know, the setup here is not very rigorous, and I'm not happy with the setup. But I don't know how to formulate a more rigorous setup. But my thinking is that maybe the patch operator should be can be more rigorously defined as a tensor product operator. You can use the tensor network to define the operator, and maybe that's a good answer. You can use a tensor network to define the generic patch operator, and that maybe became a framework, a foundation for the future calculation. So that I'm thinking that may be the good choice. And then what is a transparent? So what is transparent means? Transparent means that all the patch operator commute, but not quite commute. They commute if the boundary of a patch are far away from each other. So this is a condition. But just say boundary is far away is not quite enough. We have to also say boundary are not linked. Sometimes, like in 3 dimension, we have 2 disks, and the 2 disks may have this kind of configuration. The boundary are 2 loops are linked. Then in that case, these 2 patch operators may not commute. But otherwise, it would commute. So we have one patch like this, another patch like this, and they, you know, if they don't link like this one, they would commute. Okay, that's one point. And second one, the patch operator, it defines the patch really means a trivial topology means a line segment in 1 dimension. 2 dimension we mean a disk. 3 dimension mean a ball. So patch operator itself don't have a non-trivial topology, just a very simple open. It's a disk-like region. Okay. And when this patch operator is small, they basically local symmetry operator. So a small patch operator is just a local symmetry operator. So therefore, this condition implies that the patch operator commutes with every local symmetry operator if this location for local symmetry operator is far away from the boundary of a patch. So this is this relation means transparent. Certainly, the first relation, this relation is stronger. We require this relation, but this implies this is weaker relation. From here, you can see the transparent means the bulk of a patch are invisible from operator algebra sense. So this is just so therefore only boundary are meaningful. The bulk is invisible. So this is really therefore. So the idea for transparent patch operator really is the idea of a fractionalization. Okay. And for example, like in quantum Hall state, we can create a single electron. But we say, well, the creation of single electron, the electron can fly apart, become 3 charged 1/3 anions. Okay. So the single electron operator is like a local symmetry operator. Then is the string operator which create an anion anti-anion is like patch operator. When the string operator is very short, this is a short string operator with anion anti-anion on the 2 ends. It's like a local symmetry operator. But when you put the string operator together, then you produce a long string operator where 2 anions very far apart on the end. But the middle of the string is unobservable. Only 2 anions on the end is meaningful. So this is a way to use an operator algebra to achieve fractalization by constructing long string operator where end of string can be non-trivial anions or non-trivial symmetry charge, you know, etc. For example, in our language, all the local operators are symmetric operators. They never create symmetry charge. But however, when you put this local symmetry together for the long string operator, the end of string operator can be operator creating symmetry charge. So like this one create charge, that one create anti-charge, together they are neutral. But when they're far apart, we start to see the single symmetry charge. So symmetry charge get exposed. So this transparent patch operator have this idea. You can expose those internal fractionation or internal symmetry charge. And the one to achieve that kind of in the algebraic way, in the algebraic sense. Yeah. Okay. Yeah.
Is it always possible to construct a patch operator with a T-block? Like that depends on the type of T.
Yeah. So certainly there's a patch operator with empty block. That's always there. And this operator is called the patch charge operator. So basically, it's that it's like this the idea we have before is this ZZ operator in Ising model. Yeah, like here, Ising model. So this ZI plus 1 is a local symmetry operator. Then you multiply them together, you get this empty block operator where ZI1, ZI2, they are far apart. But each Z, a single Z is a charge operator, it's create a charge. A pair of them don't create charge. So this really like, although they have empty block, but they're really coming from the local symmetry operator, you know, in terms of the local symmetry operator, they don't have empty block. You cannot construct these two operators directly. You have to using a string of a local symmetry operator to construct them. Although formally in this particular lattice regulation, it looks like an empty block. Yeah, so it's a kind of game like that. But certainly for the domain creation operator, this one don't have empty block. Yeah, but however, how the block is invisible. The block commute with any local symmetry operator. So although have non-empty block, effectively have empty block. It's because commute with any local symmetry operator. It's invisible, effectively empty block. So that's really the idea here.
I was thinking whether like the symmetry say not internal, does it have such a block?
You mean symmetry is what?
It is not internal. Say.
Oh, yeah. I don't know. Yeah, this is I don't have a theory for the non-internal symmetry. Yeah, like translation, rotation, how to do this. I don't have it. Yeah, I wish. Yeah, this is very interesting. Yeah, yeah. That maybe that's open question. How to view this in total space-time symmetry from this point of view. Yeah, yeah. I have trouble with that. Okay. So this is a patch operator. Okay, and so let's just give some example, like in an Ising model. Okay, we have a spin flip symmetry from spin up to spin down flip symmetry. That's Z2 symmetry. Then the X operator is a symmetric, but we have to have the pair of Z is a local symmetric. So those are generator of this local symmetric operator. Okay. Yeah, I should really write the Z my plus 1 maybe. But then in 1 plus 1 dimension, then we have a string operator which ij are far apart. So that is a patch charge operator. And then we can also multiply this lot of xi together and define another patch charge operator. And that is and the single xi do not commute with zij. But when you multiply them together from a patch, then when zij is kind of near the far away from the boundary, then this operator commute with zij. So this will have empty invisible block, and so that's this is called the patch symmetry operator. Okay. In 3 dimensions, very similar, and we have a string operator which is connecting I and j with empty block. We call charge operator. And in 3 dimensions, we have a ball operator. We have our region is a ball. And then we have a operator xi, xk for all the sites inside the ball. Okay. And that can generate the patch symmetry. That's like we do symmetry transformation in this region, but not in other region. What is interesting is that in 3 dimensions, we have a other patch operator. Those one is a kind of strange, but actually it should be there. So let's consider disk operator. This disk operator have empty block, so therefore operator only live on the boundary. So therefore, this K only live on the boundary. On the boundary, what do we have? We have a projection to the Z, projection to downspin, and or projection to upspin. So this part actually project to the downspin. Okay. So we apply this operator on a boundary. All the spin on the boundary is project to down. And this operator alone is not. They do not commute with a. If this suppose if this disk is inside this ball, then the Z will be flipped by this X. So this operator alone is not do not commute with this ball operator. So you have to add another piece, which with a flip sign Z. We'll do this combination commute with this. Okay. So actually, this operator creates this one-dimensional Z2 spontaneous symmetry breaking states. We apply this operator on the boundary, you get a spin down plus a spin up. You create this one-dimensional phase. Okay. So it turns out that those operators are important. They are also part of a story, this transparent patch operator. Similarly, we can do the same thing for the ball, which is an empty ball. But the ball have a two-dimensional boundary, and this operator produces a two-dimensional symmetry breaking state on the boundary. Okay. And then in general, we can also do similar thing, creating the SPT state on the boundary in 2 dimensions. In 1 dimension, we can do SPT. And in 2 dimensions, we can also do SPT. But also in 1 dimension, we have no topological order. But in 2-dimension boundary, we can even create a topological ordered states. So that's why I'm thinking this patch operator should be this matrix product operator, which you can create all these non-trivial phase. And those operators should be there, and then the structure of all those patch operator would give us this category. The reason I include those here because the topological order in higher dimension have all kind of excitation. The including excitation given by this symmetry breaking state of a lower dimension topological order state on the membrane, like a 3D topological order have a membrane excitation. And some membrane excitation actually symmetry breaking state. Some membrane excitation are SPT state, other membrane topological order state. So those are there in the higher category description of topological order. So therefore, it's natural those operators should be also included as in our transparent patch operator, and they can be included naturally. So that also suggests maybe this picture is okay. So looks here is arbitrary. What do you include? What do you do not include? So actually, this is a key. Actually, I will mention this. You know, we have an equivalence relation between 2 transparent patch operator. You know, otherwise we have too many of them. So we say that certain transparent patch operators are equivalent. So you only care about their types. So what their equivalence relation, the most obvious is this one. That we can apply the local symmetry operator to its boundary. Like we have a string operator. We can apply local operator on this end, some local operator on this end. We will get a different transparent patch operator, but we'll say these operators are equivalent to the previous one. So this very much like we define topological excitation, anions. You know, if anion differ a little bit by local operator, they are the same. This same idea. If end of transparent patch operator differ by some local symmetry operator, we say they are the same. Okay. So therefore, those type of operator are necessary. You know, even include those equivalence relation, we should have those types, because basically we say that if a boundary is a Z2 symmetry breaking state, they belong to non-trivial type compared to the trivial one. However, you can have another empty box operator, but the boundary is some kind of symmetric product states. Then that one can be mapped to the trivial operator, identity operator, by local symmetry operator on the boundary alone. If you can do that, then that maybe is trivial. Okay. Anyway, so there's some setup here, and so basically we say that on the boundary we can create this local symmetry operator. And another thing that we can even multiply non-local operator so that two string operator are the same. But this non-local operator should be all commute with this local symmetry. So this non-local operator should be all transparent, totally transparent. Okay. Actually, this freedom really says the following. It's really that it means the string is movable. Because suppose we have two endpoints. We have one string connecting them. And we can move the string. We can move the string by this kind of equivalence. So when with different string location, it is still equivalent. So I think this maybe is enough. So this is kind of set up. So from here we can define a set of some type of a local transparent patch operator. So this type of transparent patch operator is similar to the onion type in the bulk, if that's the point. So you can see when you define bulk topological order, bulk topological have onions. Onion have a few types. How we recover those type of onion from transparent patch operator? Well, that's a way. We define transparent patch operator, define their equivalence relation, and then the equivalent class would correspond to the onion in the bulk. Yeah. So now you already start to see, yeah, there's something hopeful. Maybe this transparent patch operator probably indeed can give rise to some topological order or some set onion in the bulk. And so that's indeed the case. So in the next lecture, we'll do the further calculation because the onion not only have the type, the onion have the fusion rule, have F symbol, have a self statistics, have a mutual statistics, and all this data. So those are actual things. Okay, onion type and the fusion rule is like a conservation law. F symbol statistics are so-called actual feature for the symmetry. So all this can be computed from this transparent patch operator. So this way, we kind of from operator algebra to derive the so-called scary name non-degenerate braid fusion higher category. If I do everything completely, we can get this. But we can only do in 1+1D. So, yeah, from 1+1D example, you can already see some pictures. Yeah. Okay. So any questions? Okay. Now, so see you next week then.